Hello and welcome to our nuclear chemistry chapter. We are in our last chapter for this semester, and we only cover the introductory material in here. We won't cover all of the content within this chapter. So I'm only going to be covering slides 1 through 29 of your handout. To begin, it is very important to make sure we're pronouncing this chapter correctly. It is nuclear chemistry and nuclear reactions, not nuclear. One of my biggest pet peeves in life is the mispronunciation of this word. So please make sure that you are saying it correctly, especially if you're ever speaking to me through a video chat or in person. Nuclear chemistry. So for this chapter, it is called nuclear chemistry because we are going to be studying the changes that happen as we change the nucleus of an atom. So remember, the nucleus is composed of the protons and neutrons. And atoms that are radioactive are considered to be unstable, and so the composition of their nucleus will change. They will gain or lose protons and or neutrons. Some of the uses of nuclear chemistry are listed here on our PowerPoint slide. One of the main uses is electricity. You've heard about nuclear power plants. And the benefit of using nuclear reactions for this is that it takes considerably less material to generate electricity. So, for example, if we want to provide about 2.5 homes per year with sufficient electricity, it's going to take 2 million kilograms of coal. I can't even fathom that number, by the way. Or it's going to take about 50 kilograms of uranium-235 to power a nuclear reactor. So considerably less material. Of course, we know the dangers associated with that, but those happen so infrequently that in the long run, it's not an issue. We will talk in this section about how new elements are created. We will briefly discuss the uses of radioisotopes for medical diagnosis, treatment, and imaging. And what's interesting to note is that specific isotopes are used for specific parts of the body. We will also perform calculations so that we can understand how radiocarbon dating is performed. This is the process that's used to determine how old something is found, say at an archaeological site. So to continue our introduction here, we will start with a reminder of the notation we use for specific isotopes. So remember, when we're discussing isotopes, these are substances that change the number of neutrons in a given element. So we use this atomic notation where the letter Z, the one that's on the bottom left, represents the atomic number, and that is the number of protons. So that's what identifies an element. If you have your periodic table handy, which I highly recommend for this chapter, the number of protons, or the atomic number, is the number that's listed above a symbol. The mass number A is the number that is both the number of neutrons and protons that are in an isotope. So remember, protons and neutrons make up most of the mass of an isotope, and so that's why it's called the mass number. Some terms that we will often use or hear when we talk about nuclear reactions: protons and neutrons are collectively often referred to as nucleons because they're the particles in the nucleus. And radioactive isotopes are often called nuclides. Reminder of some specific examples of isotope notations. So here we have an isotope of carbon-12. We can write the symbol this way. We can also write it out by writing the element name with a hyphen and the mass number. So that isotope can be specified either way. So again, remember the number in the bottom is the number of protons. That is usually optional because, of course, we know if we're talking about carbon, it's going to have 6 protons. And of course, the number on top is our mass number. So that is the number of protons and neutrons. So, of course, subtracting those two would tell us the number of neutrons in that specific isotope. So, carbon 12, of course, has 6 neutrons. And my hand is in the camera. Sorry, using a different computer setup here. So carbon 13, of course, by the time we do the math, we realize that that one has 7 neutrons, and then carbon 14, we know will have 8 neutrons. In this first section of the chapter, we discuss the types of reactions and decay reactions that nuclides will undergo. And in this class, you won't be asked to predict the type of decay, but it is helpful to understand where this comes from, that it's not just a made-up thing. So first, we start by discussing how stable isotopes are. And it turns out that there are a couple of factors that determine stability. The first one is what are called magic numbers. So scientists have figured out that any nuclei that have the magic numbers listed here, whether that's protons and or neutrons, these isotopes turn out to be stable. They don't quite know why. It has to do with, as is shown over here, strong and weak nuclear forces, the interactions of those protons and neutrons. And so again, you don't need to memorize these numbers, but recognize that any isotope that has that number of protons and or neutrons will be stable. As a second factor, isotopes that have even numbers of protons and neutrons also tend to be stable. And I say tend to, that's not a rule, but the stable ones tend to have even numbers. All isotopes of the elements greater than atomic number 83 are radioactive. So again, every isotope above element 83 is radioactive. And specifically all isotopes of technetium and promethium, notice those are less than 83, all isotopes of those are also radioactive. To determine the type of radioactive decay, the natural radioactive decay that an isotope would undergo, we use what's called this band of stability. So in this band, if you can see, there are black dots in this graph. Hopefully you can see those black dots. So notice our x-axis is showing number of protons and our y-axis is showing number of neutrons. So this dotted line on the diagonal here is showing the 1-to-1 ratio. So this diagram is showing all of the colored dots of all isotopes. The black ones are the ones that are stable. The colors in here represent the half-lives of some common isotopes, but where an isotope is relative to the black dots helps determine the type of decay that would happen. And if you're checking this graph out, hopefully you actually see this interesting island of stability in the upper right-hand corner. As we get into reaction types, one of the most common questions I get is, and that you should be thinking is, why make new elements? What's the purpose of going up to element number 120, which doesn't exist yet? And the idea is that scientists have theorized, based on their understanding of stability, that eventually isotopes will reach this island of stability where instead of being created and then immediately decaying, we can make some isotopes that will fall on that island of stability that will stick around for a while, and then we can find a purpose for them. So to predict the types of decay, again, you won't be asked to do this, but just to understand how we do this, there are 3 general classes. If our N to Z ratio is too high, in other words, if we have too many neutrons, if this isotope is on the upper left side of the band, then these nuclei tend to decay by beta decay. And we'll talk about the types of decay and what they mean. If that ratio of neutrons to protons is too low, in other words, if nuclei are on the lower right-hand side of that band, then these nuclei tend to undergo positron emission or electron capture. Those both result in the same decay product. And then the last option we have is very heavy nuclei. So anything with a mass number greater than 200 are very unstable, very heavy isotopes, and they will tend to undergo alpha decay. That's the fastest way to start to get rid of substances in the nucleus. So that's our introduction to nuclear chemistry. In our next section, we will talk about the types of decay particles, nuclear particles, and decay reactions.